Let's give a video console with those of you who stay for bravery. They are brave and drunk. Well, Javier. Already? Yes. I am. Investigator, hacker, everything. You introduce yourself and let's go. Quickly. Well, how are you? Good afternoon. Well, first of all, it's always a luxury to be able to talk here at CriptoredCon and tell a few things. Well, and to do it on the CryptoRed track, without which it would have been very difficult for many of us to prosper, is a luxury. So, well, I am going to tell a research we were doing at the University of Alcalá. For those who do not know me, my name is Javier Junquera. I am a civil servant at INTA at the Satellite Navigation Systems Center, and I am a professor at the University of Alcalá, where I have been many years as a researcher of the ISDFI chair. And well, to take advantage and also to thank CryptoCert a little bit, I also went through the certification a year ago, and it is something I recommend to everyone. So, well, to summarize a lot of what the talk is going to be about and why it is a talk that has a cryptographic component, what we are going to do is using Android accessibility permissions and notions of cryptography. That's where Al-Kindi comes from his early cryptanalysis treatises to set up an Android keylogger in a very summarized way. So where does all this come from? We at the University of Alcalá were in a European project in which we had to secure medical devices, and one of the techniques we used was continuous authentication. In continuous authentication, what we do is to take behavioral biometrics, which is basically to take behavioral patterns of users, which can be many things. They can be classic biometrics, they can be forms of writing, either manually or with a keyboard. With a keyboard. In fact, we developed a virtual keyboard to take keystrokes, and with the metrics of the keystrokes, try to identify people and others. Like there is research within the state-of-the-art in which they even use electrocardiogram patterns to identify people. Well, going on this side and on the side of the use of devices, what we did mostly was use the Android API for accessibility. For those who don't know it, in Android we work with different APIs to program the applications. One of them is the one for accessibility, which in principle is designed especially for blind people who, interacting with the phone, can generate different responses to the usual system and can display actions that are not the usual ones. Among all the things that can collect this API, above all, to complement the use of the keyboard within this analysis of the behavioral biometrics of the users for what are the patterns of use of the applications and especially what are the patterns of use of the screen. This API provides gesture-related events and location-based events related to where you are working on the screen. And at the end, with machine learning models, we were able to model the user's identity. Our main interest was detecting device theft. Basically, what we did was to capture accessibility events, and within these accessibility events of those that were related to the screen, we obtained a rectangle or areas in which the user was pressing or that he was using from the screen. What happened to us? That our main target was the keyboard, but our application was a bit poorly programmed, and just the keyboard events were not uploaded to the server. So, as we were a bit embarrassed because we had worked with many users and we had had them typing with a keyboard that did not have autocorrect, which for a long time, so we tried to reconstruct what they had written to see if it would not kill us too much. So the first thing we did was to draw heat maps with the data of where the keystrokes had been occurring, and in the end, we realized that regardless of all the use they made of the phone, there was always a concentration in what could be the keyboard. With this heat map, we were able to find out where the keystrokes were. And in the end, that could translate into us somehow retrieving what they had typed, but this is trivial. Since we are a bit lazy too, well, instead of doing it by hand, we worked with K-mines to get clusters of where these events were occurring, and if we limited it to a single event, we would have to use the heat map event, and if we limited it to a specific area that is below, where the use of the screen other than the keyboard was that was not the keyboard, because we ended up getting something with which we could map those keystroke events with each of the keys. For example, what we see there is that the cluster in which the X is, then all the events that fall inside. In addition to k-means and working, with scikit-learn, it's super easy to catch all the keystrokes and all the screen usage events that were not really being captured by the keyboard, or were being captured but were not reaching us, but they were being registered as usage events from the accessibility API, so taking out what the users were typing. So in the end, what we found was that we had a keylogger of a thing that we didn't want to make a keylogger of. We had also done a privacy impact assessment for the project, and a lot of things that ended up being dismantled by this alone. What happened? Well, in the end, there were some things that were not quite right, because in the end, the determination of these clusters is not deterministic. So then we would do a little bit of post-processing, and we would get conversations like this. Hi, how are you? How are you? I'm eating cereal here. And then the text, that is, in between the text they had to write about terraplanning. People had left for conversations that had nothing to do with it. This was already a danger for our project, because in the end it broke the impact assessment and could have problems, especially with the ethics committee of the university and all these things that are not going to be recorded. But, well, we decided to think about how we could prevent this from happening. In the end, it was not something that could always be applied, because not all keyboards are the same. We know that there are a lot of different distributions, and especially being in Spain, we have a peculiar one. And we said, well, if, for example, we randomize the order of the keys, then this is fixed. If every time you open the keyboard, or when the keyboard is installed, the keys are not where we thought they were, this mapping could be useless. So what happens? So what we decided to do was to try to see if by really randomizing the keys, that mapping was going to be useless, or at least without knowing exactly what is the origin of the keystrokes, that mapping would be useless. And we worked with HMOG. HMOG is one of the most important state-of-the-art research in continuous authentication. And basically what it consists of is that they capture events from a bunch of Android phones. They put users to work with their devices, and they capture events, well, that, from the gyroscope, from the accelerometer, to try to infer what things they're doing with the phone, and get this behavioral pattern with which to model the identity of the users. And they generated a data set that is one of the best, which has also served us a lot for other things, with 100 volunteers, a lot of work time. So, taking the raw keystroke events, we decided to test our model and see if it worked, or if we could really end up blindly extracting the keystrokes. We started from the same thing we did before. Basically, when we used k-means in the first example, where we knew where the keystrokes were, we did a direct mapping of those keystrokes to the key we thought they were on. And here, since in the end for us they were random, or we didn't know what was behind them, on which keyboard they were being typed, so we decided to put them with random characters. Taking the cluster that k-means had made, we passed the screen events, the touch events on the screen, and we gave each one a random value within a charset in which they were printable characters, basically to be able to work with Jupyter notebooks. Since we came from CriptoRed as well, and we've done many years of watching CriptoRed pills, we realized that even if it was random, this was not random. In this pill, which is interesting, which is one of the introductory ones that they have on YouTube. Tell or specify a little more about the research that we were talking about, kindi. At the end, in a ciphertext, when a monoalphabetic substitution has been done, which is basically what we do when we randomize the position of the keys, each of the keys that we press, even if it is not the same as the one that would be in the original position where we expect it to be, is going to have a frequency. So doing a frequency analysis on the keystrokes or on this text that we had generated with the HMOG dataset, we knew that we could not do a mapping as we did at the beginning. That is, if it falls here, this is the X. If it falls here, this is the A. But we could find a relationship with the frequencies found in our language, in our usual language. For example, if the I has a certain frequency very similar to that of the C in Spanish, or in English in this case, which is the language in which the HMOG dataset was, we could also make a relationship between these two letters and end up getting the text. We put it to the test. The first one was fine, because in the end, the phone keyboard has a lot of peculiarities. We are not good at typing on the phone, no autocorrect or anything, so we spent some time trying to see what things were messing with this data set. One of them was mainly the issue of deletions. At the end, the statistics, when half of the letters that are being typed are useless, and when there is also a mysterious key that has no relation with those statistics that we were seeing before, such as the delete key, it was very noisy. So, one of the first jobs we did was to try to infer what the delete key was, and once we detected it, clean up the original data set. Clean up the original data set in keyboard typing or in our regular use of the phone. We type very bad things and very weird things that also break the statistics when we are comparing it with statistics of classic texts or texts that are normalized, and the statistics of the space bar, which at the end was one of the characters that was repeated the most. So once that was done, we proceeded to follow our methodology, and what we did was taking the events from the HMOG dataset. These are pulse events. There are different types of events. When you press, when you lift, when you press and press a little bit. We were also testing with the different approaches, and in the end, only with the pulse events, mapping them with k-means. Relating each of these clusters to a particular character or to some value that we could then analyze, that we could get statistics from. We would do our cleaning process, and we could go on to do the cryptanalysis. What we have on the left are the usage statistics for the different characters in English. And on the right, the usage statistics, the statistics of the frequency of each of the letters that are in this text here. This text was actually a little bit longer, because with short texts, we know that this does not work, or works a little bit worse. But, well, once we had the two frequencies, we only had to map. And, well, as we are also a little short, instead of chopping the code that did the analysis, we used a library. So with this monobreak, what we got was directly from the raw events of keystrokes and screen events of the HMOG dataset to get something like this here, that although it is a little misunderstood, when we go to the publication, to the HMOG paper and the dataset that they published, with what they had used for the users to train, we see that many of the phrases, you are not driving, you can, I don't know what, you are not driving, you can enjoy the view, and so many others were perfectly eligible. In the end, well, we were unmasking something which in this case was intended to be public, but in our case it was not. In the end, as we have seen in the example at the beginning, we were bringing up conversations that we were not supposed to have access to. And this is a little bit the result of the cryptanalysis work we did on that data set. What's going on, and what is it that worries us about this, or why? This may be anecdotal, and it was more of a game for us that entertained us a lot, but it was just a game on these data sets to try not to get killed by those who had been training us. So this can be applied to many other things. We were working with gesture events on the screen, which in the end, it is almost trivial to realize that at some point those gestures are occurring on top of a keyboard when we are on a cell phone. But what can happen if by capturing, for example, the accelerometer data from a watch or from any device that is constantly capturing data and things and sending it to a server so that just in case at some point somebody comes up with what to do with it, we are able to generate 26 or 27 different clusters that can then be mapped with keystrokes. So, well, basically the question that remains open is how many things that have passed some kind of evaluation or that have passed some kind of study related to data privacy, could we do exactly the same thing by just looking for which of the events or which of the gestures can we get out 26 clusters of characters? That is, everything is susceptible to end up being a keylogger or end up being something that we don't know what implications it may have for privacy. So, as a conclusion, I think I have been one of the most applied over time. In the end, in Europe, we have a data protection regulation that one of the things it emphasizes the most is that we have to try to minimize the collection for the use that we want to give it. And this is something that neither researchers nor, of course, commercial companies do. And ultimately, those who want to do it well, we are getting more and more efficient tools such as multi-party computation or the use of homomorphic cryptography, that if what we really want is to make a focused treatment, and that does not generate more risks than we try to avoid, for example, blocking the device with continuous authentication, then that does not lead us to places where we do not want to be. On Saturday, I am with Carlos also giving other talks about the context in which we did this with medical devices, and one of the things we are going to discuss is that how massive data collection occurs in addition to very sensitive data that in principle have no use, which in principle are only statistical, but that can lead us to very dangerous areas for the privacy of us. So nothing else. Thank you very much. Any questions? Thank you for this time. They are going to thank you a lot. Any questions? I'll plug in the laptop while I'm at it. If not, the radio is for you. Yes, 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 yes. We're no longer in control of the public. I don't know what to do anymore. Come on, any questions? For Javier? Anybody? It's just that we've teamed up for the radio, eh? Okay, well, let's close the show. Is Joanna around? Is the AWS team? Have they left too? No one from AWS? Are those of you who won the CTF here or not? Well, if there's nobody from AWS, I'll tell you. Well, very quickly, okay? Let's see if we can get it all out of the way in 5 minutes, and we'll be on our way.